Good morning, guys. Last person on Friday left the mic on, so it's dead. Can you guys hear me okay? Hopefully. I'm not sure at the back. All right, so before we begin, I just want to talk about a couple of things. First, the midterm. This is the first time I get to talk to all of you guys after the midterm, so let me just ask you guys, how was it? Good? Was it what you kind of expected? Yeah? We thought it was, I was too mean. We thought I was too mean. Really? I thought I was too mean. If you guys want full transparency, I made that midterm hard. I made it as hard as I could so that I can give you guys an easier second midterm. Second midterm, as you guys know, it's worth more. I give you guys a nice hard midterm, make you guys study hard, and then you guys do great in the second midterm. Well, you guys did great in the first midterm, so now I don't know what to do. You guys are just too smart. I kind of talked about it with the seminar students on Thursday. Midterm 2 is going to naturally be easier. Why do you guys think that is? Midterm 1 was all about linear algebra. Midterm 2 is going to be stresses, strains, and as we're going to talk about, constitutive laws. With linear algebra, Math 102, did you guys like Math 102? No, there's a lot of tricks involved with the linear algebra. I have the statistics for every question, and the worst questions statistically in the group were the ones with tricks. And that makes sense, right? Linear algebra is full of tricks. If I don't say a matrix is symmetric, like I did in one of the questions, we can't diagonalize it. And that got most of the students. But can I really pull those tricks with strain? Not really. Look at all the examples we've done in this half of the course. Stresses, calculations. Strains, calculations. Has there really been any tricks thus far? No. Because when we start talking about stresses and strains, we keep everything realistic. I can't give you some wonky scenario because chances are it's not physically possible. And that's not the goal of this course. The goal of this course is to analyze things that are physically possible. So if there's any questions about midterm 1, just let me know. But I'll be honest with you guys, again, transparency, that was a hard midterm, and you guys did better than the average last year, and that midterm was way easier. So yeah, good for you guys. Yeah. Now, one other thing that I brought up to the seminar session, and I want to know what you guys think, is for midterm 2, would you like more calculation-based questions, numerical questions, rather than multiple choice? It's a trade-off, because again, it's numerical, it could be anything. But here's the good news. For a numerical question, where I just ask you to input a value, could I hit you with all of the above, none of the above, not enough information is provided? I can't. And I know that those are the ones that students hate the most. So I'm not going to ask you guys to decide now, but something to think about. Would you like numerical questions on midterm number 2? Just think about it. All right, so that's the midterm. Any questions concerning the first midterm? You guys all did great. Very proud. All right, no questions? Great. Now we're going to talk about the assignment. Now the assignment that's already kind of in the works this week has to do with strain. And I've gotten maybe 4 emails now about significant digits. And at first I didn't quite understand. I didn't. Because what would happen is the exact answer would be something like this. Oops, that's the eraser. 0.019483, whatever. And then students will go 0.019. Clayton, how dare you? This marked me wrong. But it's the same thing. When it comes to strain, is that the same thing? No. And it's one of those things that I can feel the passive aggressiveness of the emails I was sent. How dare you mark me wrong? That is the exact same thing. So I told them, yeah, you know what? If you guys want, I will give you the marks. Because then I realized it's not your fault. Do you guys know typical strain values for anything? What's the crushing strain of concrete? I heard it. You're not supposed to answer. You guys are supposed to not know. But the reality is I need to take a step back and realize you guys are third and fourth years. How many of you guys know how to design? No one. How many of you guys have taken 2 classes in design? Just 2. No one. So this is why I kind of say, you know what, I will give you the full marks if you guys are really insistent, because I don't want to ruin your Thanksgiving weekend. But it's something to note that this is actually quite important. Those 2 values, if I were to use that second one in design, it could be terrible. Look at the difference between them. It's approximately, what, 0.0005? That could be quite a bit. Quite a bit. Now, I'm going to give you guys an application where this was quite a bit. You guys ever heard of pre-stressed concrete? Who's heard of it? Who knows what it is? All right, a couple of you guys. Pre-stressed concrete, as you guys may know, well, actually, let's just draw a picture. If I were to have a concrete beam, is concrete good in compression? Yes. How is it in tension? Absolutely terrible. So what we do is we put a piece of steel, oops, come on. There we go. We put a piece of steel at the bottom. The top is in compression, which is good for concrete. The bottom's in steel. Now what happens in pre-stressed concrete is we take that steel and we pull it. And what that does is it puts the whole section into compression, the entire concrete section. It's actually beautiful. In pre-stressed concrete, we don't have steel that goes horizontal like this. It's kind of more parabolic shape, like this. And we pull it. Because if I have that shape and I'm pulling that steel, as you guys can see, that steel's going to push upwards. You guys can see that? The steel, once I pull it, is going to want to start going like this. Now, what actually happens is if I were to have a beam here, and if I were to have a distributed load on the beam, let's go green. So distributed load. What you guys will actually see if you design pre-stressed concrete correctly is you can have it so that your tensile force in the steel completely counteracts whatever load you apply on it. So all those bridge girders you see, they're all pre-stressed. You design them in such a way that the beam itself is almost experiencing no load. Because all the load applied by the cars is counteracted by that steel pushing back up. It keeps the entire section into compression. And that has a lot of extra benefits. Why do you guys think I would want the entire concrete section for a bridge girder in compression? Basically, another way of asking is why is it bad if I were to have cracks at the bottom of my beam? Why would that be so bad for an outdoor scenario? Water. Does steel corrode? Yeah. Yes. And imagine if that steel that's holding up that entire beam, poof, gone. But then you guys think, Clayton, what are we doing? We're not talking about pre-stressed concrete. We're talking about strains. This is what I'm getting at. When I have a beam and I were to take its steel, pull it, it's going to compress the beam. Is that going to put strains on my beam? Yes. There was a bridge down in Florida, pedestrian bridge, crossing, I think it was an interstate, something like that. And when they designed it, they didn't account for that additional strains due to pre-stressing. And it was tiny. It was even less than that. Less than that. What do you think happened to that bridge? Collapsed on the road. Killed people. So it's one of those things that, again, you guys haven't taken design classes, so you guys don't really know strains. But this is why adding those extra figures is actually quite important. I know when I mention strains, to me, they're all magical, but to you guys, they're just a number. Like, who really cares? It's just a small number. But it's very important when we talk about strains because in structural design, they can be extremely, extremely important. You guys understand why in the assignment it's important now? I want to give you guys context. I don't like just saying, well, you have to because the assignment says so. Of course not. If that was the case, I would accept that and not even care. I want to try and give you guys context to everything that we're doing. Strains can be extremely important. So that's kind of a little bit of background. Now let's go into today's lecture. Stress measures and failure criteria. This is going to be a good one. This is going to contain a formula that you guys will see everywhere. How many of you guys have heard of the von Misi's stress? Von Misi stress. All right, couple, great. For those of you who don't, I'm about to change your lives. It's going to be absolutely beautiful. So stress measures. When we talk about stresses, there's a bunch of different ways. Think about strains. We didn't just have one way for strains. We had a bunch. We had the green strain, small strain, engineering strain, true strain, whatever, so many. When it comes to stresses, there's a lot of different ways we measure it too. The nice thing about stresses is the measures are actually quite simple. You guys are going to see this on your assignment this week. The first one is the hydrostatic stress tensor. So what's going to happen in these kind of questions, I'm going to give you a stress tensor. And from last week, I can ask you for a traction vector. I can ask you for normal stress as well as shear stress. 3 things. And the formulas were actually all quite nice. So it didn't even matter. The next thing I can ask you for is the hydrostatic stress tensor. Now, when you look at that, that looks scary. That doesn't look like something that's going to be nice, but it's actually extremely simple. The hydrostatic stress, which we denote as small p, is a scalar representing the average normal stresses on a face of an infinitesimal cube. What is the average normal stress? Well, if this was my Cauchy stress tensor, again, 6 components because it's symmetric, P, the hydrostatic stress, is just going to be sigma 1, 1 plus 2, 2 plus 3, 3 divided by 3. That's it. Question for you guys. What is this right here? The sum of the diagonals. The first invariant, trace. So if I want to, and I want to find this hydrostatic stress P, all I have to do is take the trace of sigma and divide by 3. Am I scaring you guys yet? No. You guys are saying add 3 numbers, divide by 3. Most of the time I can do that. The only thing that I've ever seen students get wrong is dividing by 3. That's it. Just make sure you guys divide by 3. You guys will be fine. So let me ask you guys really quick. This right here is our normal state of stress. Now, our stress tensor is symmetric, meaning that we can diagonalize it into its principal stresses. All right, hopefully I'm not losing you guys. If I give you guys the principal stresses, so I'm going to have 1 here, 1 here, 1 here, and the rest are zeros, can I still use this formula for the principal stress tensor? Who thinks yes? Who thinks no? The answer is yes. I know, I'm sorry. The reason why is because the trace is an invariant. It doesn't matter how much you rotate it, anything like that. The trace of a tensor is always going to stay the same. So if we look at the formula and the top stays the same, is 3 ever going to change? No. So this will always stay constant. So remember, the trace here is an invariant, meaning that it'll remain constant no matter what basis set is selected. So if I try and trick you guys and say, oh, I gave you guys the principal stress tensor, please don't try and back calculate the actual Cauchy stress tensor. You guys can just still use the exact same formula. It's a piece of cake. Now, yeah, this is just saying the same thing. You can calculate this from either tensor. The answers are going to be the same. If they're not the same, make sure you guys know how to add. That's the only real advice I can give you guys. So this is the hydrostatic stress. Now this right here, is this a scalar or a tensor? Scalar. Add 3 components, divide by 3, this will just be a number. But if you look up here, I'm talking about the hydrostatic stress tensor. How do you think I get that? You think it's going to be some crazy equation? Who thinks it's going to be a crazy equation? No one? You guys have too much faith in me. The hydrostatic stress tensor is just going to be that hydrostatic stress P from above multiplied by the identity matrix. So it's just going to look like this right here. Now this was important because if you guys remember back to last week, we did an example and we had a tensor that was in this form. So all three components were the exact same and the rest were zero. And we said, is there a plane? So can I rotate this so that I can get some shear? Were we able to get shear from this tensor? Who remembers? Yes. No. I'm so sorry. I feel so bad when I set you guys up. For hydrostatic stress, we can never get shear. What was no was if I were to take this P right here and get rid of it. So let's say that I had 20, 20, and then 0. Can I get shear with that tensor? Yes. When all three are the exact same, I can't get shear. And I'll show you guys why a little bit later on. So this is the hydrostatic stress tensor. It's going to be in your assignment this week. Are you guys confident you guys can calculate the hydrostatic stress tensor? Perfect. Who knows what it means? Why do we care about this? No one knows? Good, because I haven't taught you guys yet. Next slide, I'll show you guys. The second one we have is the deviatoric stress tensor. Now, when you see a name like this, do you guys think it's going to be a crazy formula? You guys are wrong. It's actually just as nice. The deviatoric stress tensor is obtained by subtracting the hydrostatic stress tensor from the previous slide from our stress tensor. So S, which is our deviatoric stress tensor, is going to be sigma minus P times I. Was P hard to calculate? No. I is the identity matrix, and all you do is subtract it. So this would be the formula, and at the end of the day, you're going to get this. As we can see, this deviatoric stress tensor, which is the same as our stress tensor, except for minus P on all the diagonal terms, as we can see, it's closely related to our hydrostatic stress tensor. Right? You guys see that? It must be closely related. So when we talk about what happens to an object, we can define what happens to an object based on these two tensors. And then the invariance of this is going to be 0. I guess that's a little fun fact. This is used for a derivation that I'm going to show you guys, but honestly not too much else. So the question is, what is the significance of these two tensors? Well, if we were to look at this tensor right here, where we have something in all diagonals and everything else is 0, we actually talked about it a little bit in strain. A little bit. We said that a tensor like this is responsible for expansion and contraction depending on what the diagonal values are. So the hydrostatic stress tensor is responsible for changing the volume of a body. If I were to take this as my body and I were to put hydrostatic stress, it'll start expanding, it'll contract, it'll do whatever. So if this is responsible for changing the volume of a body, what do you guys think the deviatoric stress tensor is for? The shape, exactly. The deviatoric stress tensor is responsible for changing the shape of a material while keeping the volume constant. This is why we distinguish these two. When we talk about this course, it's always going to be linear elastic, meaning nothing is going to start damaging, nothing's going to break. So the significance of the deviatoric stress tensor actually doesn't play a big role in this class. But after things start to break, we know that the material curve starts to change. We call that plasticity. When you guys deal with plasticity and you ever want to calculate anything using plasticity, this plays a huge role, this deviatoric stress tensor. All of plasticity is actually governed by this. And I'm going to show you guys a little bit later on where it comes in. So this is the significance of those two tensors. Now, question for you guys in the assignment this week. First question, hydrostatic stress tensor. You guys said it's easy. Second question is deviatoric stress tensor. Also pretty easy? Yes. Hopefully you guys have no trouble. Again, this is going to be important later on. I put extremely important, but these notes were taken from the graduate course that I teach. So for you guys, it's not extremely important, but it's kind of important. Yeah. So that was two stress tensors. Now we're going to talk about von Mises stress, and this is going to be the big one today. You guys will be asked about von Mises stress till the end of the course. I promise you guys. The von Mises stress is going to be a single value. Notice how it doesn't say tensor up here. It's just the von Mises stress. Before I talk about it, I just want to show you how important it is. How many of you guys have used a finite element program? How many of you guys have simulated something? I'm not expecting a lot, but maybe a Dean's Research Award somewhere. No? No. So what happens, no matter what program you use, there's a bunch. There's OpenSeas, ANSYS, Abacus, whatever. If you guys run your program and you get your results, it's going to show you the stress distribution. That's why we simulate things. We want to find locations of maximum stress, if it fails, etc. As you guys will see, there's going to be different types of stresses you can look at. There's going to be principal stresses. There's going to be shear stresses. There's going to be sigma 1,1, sigma 2,2, whatever. But the default that they will always show you in any program first is going to be the von Mises stress. It's going to be, again, perhaps the most important. Now the question is, all right, Clayton, you're really hyping this up. What is this von Mises stress? Well, what I'm going to do is I'm going to give you guys an example. We have a potato. And I'm interested in knowing the material properties of this potato. So let's say, okay, I go to the structural lab, and I can put it under uniaxial tension. So sigma 1,1 on both sides, pull it apart, and then I go to the lab techs, and they say, okay, here's the curve of the potato. Now, question for you guys, is this uniaxial or triaxial? Uniaxial. We're just pulling in one direction. It's the same thing we do with steel. And we get this curve. Now, what's nice about this curve is we can see that there's a point here where we call the yield stress where the behavior starts to change. I made this almost identical to steel. It's elastic, it hits a point, and then it starts going or undergoing strain hardening. But as we can see, there's a point here in which it yields. Now, let's take this case right here. Let's say sigma y is 400 MPa. 400 MPa. If I were to apply 200 MPa to my potato, is it going to yield? No. 200 MPa is somewhere down here. It's below our yield stress. We're good to go. If I were to apply 600 MPa, is it going to yield? Yes. See how obvious it is? It's yes, no. All you have to do is compare the two numbers. What happens when I give you this state of stress? I tell you, oh yeah, this is 400 MPa, and then I give you the 6 different stress components in 3 dimensions. Can you tell if it's going to yield? No. It's very, very difficult. Now the problem is this is nice and easy in the lab, so it's very easy to obtain this curve, but is this realistic? Is this roof you guys under, is this just under uniaxial stress? No, it's under a 3-dimensional state of stress. So what we do is we use the von Mises stress to take all of my stresses that are on a cube in 3D, and it converts them into an equivalent uniaxial load. So what I would do is I would take all my 6 stress components. I can find my von Mises stress, which let's say is 300 MPa. And then I can compare it to this uniaxial curve. So again, yield stress is 400. Let's say I find the von Mises stress as 300. Is this going to yield? No. 400 MPa, and if my von Mises is 300, it doesn't yield. So this is the whole goal of von Mises stress. It takes our 3-dimensional stress state and it converts it over into a uniaxial stress state so we can actually say, okay, does it yield, yes or no? Now, as you guys are going to see, the von Mises stress is only going to be one type of failure criterion that we use. There's going to be a bunch. So this is the von Mises stress. So again, it's easy to see when the potato will yield. In this case, not so easy in 3 dimensions. So what we do is we use the von Mises stress measure. It's based on the Cauchy state of stress, and it provides an equivalent uniaxial stress. So you say, okay, Clayton, I know what it means now. What's the formula? Now I'll ask you guys. Von Misi stress, who thinks it's going to be a nice formula? Who thinks it's going to be ugly? It's going to be a little bit ugly. I'm not going to lie to you guys. So the von Misi stress is a function of the second invariant of the deviatoric stress tensor. Meaning the von Misi stress is the square root of -3 multiplied by the second invariant of our deviatoric stress tensor. I'm showing you guys where it comes from, and I'm keeping the proof minimal. I'm not going to show you guys where it comes from, but this is the formula. This will not be the one that you guys use. But this is important because I said for plasticity, we use the second invariant. If you guys go look at plasticity textbooks, the most commonly accepted form of plasticity or theory is J2 flow theory. And the first question I always get asked in final element, why J2? 2, the second invariant of this. Now, do we have a formula for the second invariant? Yes. So I can take that formula and substitute it into here. Now, when we talked about our deviatoric stress tensor, I said one little fun fact is the trace is equal to 0. Invariant 1 of S is equal to the trace, which is equal to 0. So this formula right here simplifies into this right here. Now this actually has quite a bit of significance, but we're not going to talk about it in this course. This is more of a graduate course when we start talking about solid mechanics. What I'm going to do though is I'm going to take S and I'm going to substitute what S is. Just keep in mind that our deviatoric stress tensor is a component or is a function of 7 things. 6 stress components, sigma 1, 1, sigma 2, 2, etc., as well as our hydrostatic stress. So what I'm going to do, I'm not going to show you guys because it's absolutely disgusting, but I'm going to substitute that all in. And as you guys will see, this is the formula for the von Misi stress. This is the formula that you guys will use. In your assignments, it's going to say what is the von Misi stress. This is the formula you guys are going to use. Is it nice? No. But there's some fun facts about it. The first one is this. I said that S, the deviatoric stress tensor, was also a function of hydrostatic stress. Does hydrostatic stress appear here at all? No. So what do you think if I were to subject this podium to hydrostatic stress? What's my von Misi stress going to be? 0. So there are some, I don't want to say limitations because under hydrostatic stress, it's usually pretty valid, but there are some things you need to be aware of. So when it comes to your assignment and you guys have to calculate this, it's not going to be nice because look at the formula, but all you guys have to do is plug things in. There isn't really any tricks. All right? We take the difference between the principal, not the principal, but the normal stresses squared plus 6 times this, divided by 2, etc. Another quick question for you guys. Can my von Misi stress ever be negative? No. It'll never be negative. So those are kind of some fun facts about the von Misi stress. We're going to go through it a little bit later. So the last thing I just want to say is, again, we use this to figure out yielding. What we do is we substitute all of our stress components in, we find our von Misi stress, and then we can compare it to our yield stress. And if it's greater than, it'll be yielding, if not, etc. It's not too bad. Compare it to the uniaxial yield stress, sigma y. Now, a different measure that we could use, because there's always more than one, is the maximum shear stress. So in your guys' assignment this week, you're going to be asked to check 2 different criterions. The first one is von Misi's. Simple. All you guys do is find the von Misi stress, compare it to the yield stress, not too bad. The second measure is maximum shear stress. This is called the Tresca criterion, and I'm going to talk about it a little bit later. Now, for the maximum shear stress, it's pretty simple. We say that in material yields, if our applied shear stresses exceed the maximum shear stress. Question is, what is the maximum shear stress? Well, the maximum shear stress is going to be this formula right here. It looks really simple, but there's one trick. The maximum shear stress is going to be the maximum of sigma 1 minus sigma 2 divided by 2, sigma 2 minus sigma 3 divided by 2, or sigma 1 minus sigma 3 divided by 2. What do you guys think the trick is here? There's one trick to this formula. If you guys know it, you're good to go. If you don't know it, it's going to be a bad time. Did I use sigma 1, 1? Did I use sigma 1, 2? When I use Roman numerals like this, what is that? Who remembers? Principal stresses. That's the key. This right here involves principal stresses. So if you guys are ever trying to find the maximum shear stress from your Cauchy stress tensor, the first thing you guys have to do is find the eigenvalues or the principal stresses. That's the big trick. Sigma 1, sigma 2, and sigma 3 in this case are the principal stresses. So you guys are saying, okay, Clayton, if I know the 3 eigenvalues, all I have to do is find the difference between them, divide by 2, easy. Well, let me ask you guys this. Why divide by 2? Why does this formula even work? That's the question. So let's look at why this formula is the way that it is. So why? Well, if I were to take a block and I were to put it under principal stresses, so just like this, 2, 3, shear stresses are 0, and I were to rotate it, am I going to develop shear stresses if I were to rotate it? Yes. So if I were to rotate it, let's say 45 degrees, as we can see, some shear stresses develop. So I got 0.5, 0.5. Now, if I were to rotate it back another 45 degrees, so basically rotate this 90 degrees, are my shear stresses going to appear? No, because if I rotate it 45 degrees, it's still in line with those eigenvectors now. We aligned it back. All I'm trying to get you guys to see from this right here is that if I were to have principal stresses and I were to rotate it 90 degrees, it's still going to be principal stresses. So we know that our maximum shear stress has to be between a rotation of 0 degrees and 90 degrees. It has to be somewhere in between there. Who thinks it's 45? All right, who thinks it's not 45? Turns out it is 45. But you're saying, Clayton, why is it 45? Well, we're going to get into an example. Again, the only thing I want to show you guys is when we rotate it, we start to develop shear stresses. But when we rotate it 90 degrees, well, the shear stresses disappear. But why is it 45 degrees? Well, let's take a very simple scenario in 2 dimensions. If I were to have a principal stress tensor of sigma 1, sigma 2, 0, 0, and I want to rotate this, I can create a counterclockwise rotation matrix, and I can transform this using this matrix. Now, did I put any values for theta? No, I'm just going to keep it as theta. So if I were to do this, and I were to transform it using our transformation formula, I get this right here. So as we can see, we have our normal stresses, and we have our 2 shear stresses. Let's see how much you guys remember first year. If I have an equation for shear, which I do, nice equation for shear, and I want to maximize an equation, find the maximum, what do? Eigenvalues? You're so used to eigenvalues, it just seems like the right answer. If I were to give you guys just a random function, derivative, exactly. If I want to find the maximum of a function, I take the derivative. So if I have my shear stress component in formulaic form, and I want to find when it's maximum, I take a derivative. So what I'm going to do is I'm going to take the derivative of this with respect to theta and set it equal to 0. Again, I'm just trying to find the maximum. If I were to do this, I say, okay, here's my formula, taking the derivative with respect to theta. And what happens is you guys get this formula right here. Cosine squared of theta is equal to sine squared of theta. Now, what is going to be my value for theta that makes this true? Between 0 and 90 degrees, of course. 45 degrees. So we know that theta is going to be equal to 45 degrees. Now, if I were to take this right here, I know that this is when my shear stress is maximum, and substitute it back into my shear stress formula, I get sigma 1 minus sigma 2 multiplied by sine 45 multiplied by cosine 45. What is sine 45? 1 over root 2. What is cosine 45? What happens when you take 1 over root 2 and multiply it by 1 over root 2? 1/2. And this is why it's divided by 2. Starting to all come together now, right? Looking nice. And what we can do is we can repeat this for the other components to basically derive this formula for every sort of way. Do you guys need to know derivations in this class? No, you don't. All you guys need to know is the formula, which was on the previous page, and this little piece of information. All right? It's in one of the examples, which I'm not going to cover, but it could prove useful. If I were to give you guys principal stress tensor, sigma 1, sigma 2, sigma 3, the rest are 0, and I were to say transform this tensor to a location or to an angle where the shear stress is maximum. How do we do that? If I were to give you guys, let's go to here. I'll go to red. If I were to give you guys a stress tensor full of the principal stresses, so sigma 1, sigma 2, sigma 3, the rest are zeros, and I were to tell you guys to rotate this matrix or transform it so that the shear stresses are maximum, what do we rotate by? 45 degrees. That's it. Do you guys know how to rotate things using Q? Yes, well, at least I hope so. You guys are experts on that. So if I ever give you a tensor and ask for the tensor where the shear stresses are maximum, you just have to transform this by rotating at 45 degrees. That's it. Yes?
On the maximum shear stress line,
Yep.
you rotate it by 90 degrees. Why is it
Oh, this one?
no on the other side?
Yeah.
Why is the stress sensor the same? Why didn't we switch?
It's because of how we define it. So again, when we define these components, it's all about how we enter them. If you were to switch it, it'd be the exact same as long as you define which one's which. So since I did change the color, I probably should have changed it, you're right. But it's one of those things that I don't want you guys to get worried about where to put things because they're all technically correct, as long as you define it with the coordinate system. Great question, great question. So that's maximum shear stress. All you guys are going to do is go to this formula. The only trick, make sure that you guys are using principal stresses. I've seen so many students just use sigma 1,1 and sigma 2,2. Don't get it right. There's a bit of a problem. All right, so is there any question about shear stresses? Because now we're going to talk about the Tresca yield criterion. Let's go forward. Any questions? No? You guys are good? Happy? Perfect. All right, so the Tresca yield criterion. This one is what we said is we want to make sure, or we state that yielding occurs once the applied maximum shear stress exceeds the maximum shear stress of the material. This is a bit problematic, just one thing that makes this a pain. When we did von Mises yield criterion, which we're going to cover again in the next slide, we said all we need to do is find our von Mises stress and compare it to our yield stress. When we test things, that's what we have. We have the yield stress. So I can find my maximum applied shear stress. We have that nice equation. But are we comparing that maximum shear stress to the yield stress? No. We're comparing it to the maximum shear stress of the material. That's not something we're given. We're given the yield stress. We're not given the maximum shear stress. So here's where the trick comes in for the Tresca yield criterion. If we look at this equation, we can take our applied stresses from our Cauchy stress tensor and compare them to the maximum shear stress of the material. Problem is we don't really know what this is. We're given sigma y. We're not given tau max of the material. But we can actually find a nice relationship between tau max and sigma y. How do we do that? Well, we're going to consider a uniaxial case. So let's say that I have my bar or whatever under uniaxial stress, and I take it to the yield stress. All right, I take it to the yield stress. So sigma y, everything else is 0. Is this right here technically the principal stresses? Is this the diagonal matrix? Yes. So can I use this formula on this matrix right here to find the maximum shear stress? Exactly. So that's what we're going to do. My tau max of my material is going to be the exact same formula as above. And when I substitute values, we're going to have sigma y minus 0, 0 minus 0, and sigma y minus 0. So of course the maximum is going to be sigma y, and then we divide by 2. So the maximum shear stress of the material is going to be sigma y divided by 2. This is the trick. When using the Tresca yield criterion, you find your maximum shear stress using this, and then you compare it to sigma y divided by 2. That's the trick, divided by 2. A lot of students have no problems using this formula. They find it, they compare it to sigma y, and they say, oh, it doesn't yield. It's sigma y divided by 2. That's the big trick. You guys know that. You guys are good to go when it comes to the Tresca yield criterion. Now, something to show you guys, which is kind of fun, but you guys won't be tested on, is all of these different criterions actually create what we call a yield surface. So if I were to take a plot, a 3-dimensional plot of my principal stresses, and I were to plot the Tresca yield criterion, I'm actually going to get a hexagon. This is very fun. We use this a lot when we talk about solid mechanics. Now this hexagon signifies a lot of things. If I were to have a point inside of my hexagon, let's say right there, has it yielded? What do you guys think? My point right here, that's inside of the hexagon, has it yielded? No, it's considered safe. If my point is right on the surface of the hexagon, has it yielded? It's just starting to yield. Here's where the fun comes in of solid mechanics. What happens if my point is outside of the hexagon? Yielded? It's actually impossible. What happens is we always start from a state of no stress. Look at this table. There's no stresses on it. I come to it and I say, okay, I'm going to stress it. So I'm pressing down, and my stress is going to increase. So what's going to happen when we talk about solid mechanics, well, I guess we're not going to talk about it, but later on you guys might see it, is the stress is going to start increasing. So it's going to be in, and then it's going to hit the surface. What do you think happens when it hits the surface? What do you think we do? We start expanding the surface. So let's say that my point somehow is here. It'll take my surface and it'll actually stretch it out. And this will be my new yield stress. It's something that, again, you guys don't need to know, but I always think it's kind of fun. You guys think, what a loser, but whatever. I don't really care too much. So this is called our yield surface. Again, you guys don't really need to know too much about it. The von Mises yield criterion, it's the easiest. All you guys need to do, find your von Mises stress and compare it to the yield stress. If our von Mises stress is greater than or equal to the yield stress, it's yielded for your guys' purposes. If we were to look at the yield surface of the von Mises stress, you guys think it's going to be a hexagon? Nope, it's going to be a cylinder. This is actually a cylinder in 3-dimensional space. How do you think this compares to the Tresca yield criterion? You think it's going to be some similarities when I put the hexagon on top? Yeah. As you can see, they have the same points at the corners. Now, when it comes to design, one of the things we talk about is conservatism. Do you guys know what that means? What does it mean? If I'm being conservative with one of my answers or designs, what am I doing? Over-engineering, exactly. Which one of these two, Tresca or von Mises, is more conservative? Who thinks von Mises? Who thinks Tresca? It's Tresca. Because let's say I had this point right here. Is this point yielding under Tresca? Is this outside of my yield surface? Yes, so this would be yielding. But this same point under von Mises, is it yielding? No. So Tresca is more conservative. Tresca, as you guys will see, this was used even in the 1800s. This was kind of one of the first attempts at creating these yield surfaces. Von Mises is more defined. And the reason why it's nice for us is because it's smooth. Doesn't that sound weird? It's smooth. Why is that so nice for us, that it's smooth and doesn't have these jagged corners? Easier for the computer. Would you guys rather define one function or 6 different functions, depending on where it is? It makes it very nice for computational programming. Now, we're just going to leave off with 2 kind of fun facts about the criterions. They do not differentiate between tension and compression. Can I get a negative from my von Mises? I can't. Is steel identical for compression and tension? Steel. Yeah, so does that matter? Not really. What about for concrete? Is concrete different in tension and compression? Does this become a bit tricky when we deal with concrete? Yes. So it turns out that concrete doesn't really use von Mises. We have to make it more advanced. Another thing about concrete that makes it even tougher, and I guess this is the second point, they're independent of hydrostatic stress. Concrete is dependent on hydrostatic stress. So it's kind of the worst of 2 worlds when you model concrete. And the reason why concrete is because if I were to take concrete, again, it's a bunch of rocks, and they're together. If I were to do hydrostatic stress and compress them, is my bond between the rocks stronger? Yes. If I were to pull it apart a bit, is my bond between the rocks weaker? Yes. So concrete actually makes these, makes it both really terrible, but it's still very good stress measures for us at least. So we're going to get into some examples now. Is there any questions concerning these 2 yield criterions? No? Everybody's nice and happy? Perfect. So let's go on over. Do this right here. So question 1, this is the only question I'm going to do. In case you guys don't know, on eClass, the quizzes, they have many more questions than just this. So if you guys want extra practice, go to eClass, there's a bunch. And I have solution videos up so you guys can watch me do it, I guess, if you want. I only do a select few in class because of time constraints. Actually, that leads me to a very juicy question, because this is something there's very few times where I've disagreed with Dr. Sammer, but this is usually one of them, so I'm going to ask you guys really quick. Dr. Sammer's approach for this class was much different. He didn't cover any theory in class. He just did examples. He said, the videos are online, you guys watch the theory, and you come to class just for examples. Which one would you prefer? I prefer to give you guys theory and then do examples, but he just examples. And I've always been curious, what do the students prefer? Who prefers just examples? Watch the theory on your own. Who prefers theory and examples? Who prefers just theory? No one prefers just theory. All right, no, good, then I'm doing something right. So it says for each stress tensor, we're given 3 of them, determine the hydrostatic stress, the von Misi stress, the maximum, mid, and minimum principal stresses, and the maximum shear stress. So if we look here, all the tensors are almost identical, but I start adding 5s to the diagonal. So this is 5, 0, 0, this is 5, 5, 0, and this is 5, 5, 5. Are one of these tensors hydrostatic? Which one? A, B, or C? C. So are you guys expecting some special things to happen in C? Yes, you guys should be expecting some very special things to happen in C. So we're going to go down, and we're going to say, okay, the first one that we want, I'll keep the up there, I guess we'll go part A, and this is the hydrostatic. That's a long word. Hydrostatic stress. Now, we know that the hydrostatic stress P is just going to be the trace of sigma all divided by 3. That's it. All we're doing is taking the trace of these tensors and dividing it by 3. So I'd say, okay, well, P, again, hydrostatic stress, for tensor A is just going to be the trace. So I'm going to take the sum of the diagonal components, just those diagonal components, and then divide by 3. So we're going to have 5 plus 0 divided by 3. If you guys throw that into your calculator, you guys get that this is equal to 1.67 MPa. Easy. Anyone have trouble with hydrostatic stress? As we can see, it's not too bad. If I were to scroll, well, actually, I guess I can't really scroll down. It's my fault for writing so big. PB, for the second stress tensor, what's my trace going to be for PB, the tensor in the middle? What's my trace of this going to be? 10. 5 plus 5 plus 0. So we go down here and we say, okay, this is going to be 10 divided by 3. And then you get that this is equal to 3.33 MPa. How about for C? What's the trace going to be? 15. 15 divided by 3? 5. Did I even need to use the formula to figure out what P is in this case? No, it's already hydrostatic, so it's going to be 5. So if you guys want, I'll write it down. P of C is equal to 15 divided by 3, which is equal to 5 MPa. So any questions about the hydrostatic stress? Should be nice, simple. All right, you guys are happy? Perfect. So we're going to come down, and we're going to go back up to the tensors a little bit later. We're going to do the von Misi stress. So I'm going to write the formula for this. It's going to be sigma 1,1 minus sigma 2,2 squared plus sigma 2,2 minus sigma 3,3 squared plus sigma 1,1 minus sigma 3,3 squared. Put the square root over top. Divide everything by 2. Now you guys may be saying, Clayton, you forgot the shear terms. Remember that this actually carries on, and it's plus 6 times all of the shear components squared. Why did I ignore all of the shear terms? Well, if I scroll up really quick, do I have any shear terms in any one of these tensors? Any shear? No. So I just simplified it to make it easier. So we're going to come down and say, okay, for A, tensor A, sigma 1,1 is 5, 2,2 is 0, and 3,3 is 0. Okay, so let's remember those values. We're going to come down and say, okay, sigma von Mises is equal to, and this is for A, sigma 1,1 we said is 5, sigma 2,2, 0. And we square that. Then you say, okay, plus sigma 2, which was 0, minus sigma 3, which was also 0, squared, and then plus sigma 1, which was 5, minus sigma 3, which is 0, square that, and then you divide everything by 2. Who knows what this is equal to? 5. 5 squared, 50, or 25, plus another 5 squared, that's 50, divided by 2, back to 25, square root 25, 5. Now this is interesting, because what does the von Mises stress do? Why do we use the von Mises stress? Exactly. It takes our three-dimensional stress state and converts it to a uniaxial stress state. If we were to scroll up and look at A, is this already a uniaxial stress state? Yes, I'm just stretching sigma 1. So what did you guys predict the von Mises stress should be? If it's already in a uniaxial stress state, it should predict 5, because we're just converting between the two. If we look at our answer, we got 5. So I'm just going to put A there, kind of down in the corner. All right, so that's going to be for A. We're going to go sigma von Mises now for B, and it's just going to be the exact same thing. So sigma 1 minus sigma 2, well, one was 5, the other was 5, plus sigma 2 minus sigma 3, well, 5 minus 0 squared, plus sigma 1 minus sigma 3, 5 minus 0 squared, divide it all by 2. What is this going to be equal to? 5. 5 MPa. If my yield stress was 6 MPa, did my material yield under that biaxial stress state? My yield stress was 6 MPa. No, because 5 is less than 6. So this is what we do. We compare our von Mises to our yield stress. If we were to go right back up, and I were to say, okay, oops, did this yield? Who knows? But now I say, okay, if I were to give him the uniaxial 6, and I were to come down, and I were to calculate it as 5, well, 5 is less than 6, it didn't yield. We're going to talk about that kind of in the next example. The next one is fun. We're going to go up here, sigma c. So sigma c, 1, 2, and 3, they're all equal to 5, all of them. So we're going to come down here and say, okay, my sigma von Mises for C is going to be equal to 5 minus 5 squared plus 5 minus 5 squared plus 5 minus 5. Divide it all by 2. What's this going to be equal to? 0. 0 MPa. Remember, hydrostatic stress doesn't contribute to the von Mises stress at all. All right? Lots of fun. Gonna go back up. Just trying to see time constraints. Yeah, I think we're gonna move on to the other examples and we'll come back, because this is kind of what you guys want for the assignment. So these are the typical things you're gonna find in exams. I'm gonna give you a scenario where something is loaded, and I want you guys to basically tell me, did it yield or did it fail? Yes or no. In this class, we consider yielding as failed. Realistically, it's not really true, but for this class. So it says, determine the vertical stress the cylinder below can withstand if the maximum von Mises stress the sample can withstand is 600 MPa. So this is my maximum von Mises stress. And I'm given sigma 22, so I'm compressing it, and I'm given sigma 11, sigma 33 as negative 200 MPa. So I'm constraining it from the sides. This is almost the equivalent of saying that 600, this is my yield stress. So question for you guys really quick. If I were to tell you that the yield stress of this cylinder was 600, and I didn't have any lateral forces, just purely sigma 22, what would sigma 22 be when this fails? 600. Now that I put lateral forces, do you think that this is going to be more than 600, equal to 600, or less than 600? Place your bets. Who thinks it's going to be more? Who thinks it's going to be less? Who thinks it's going to be equal to? All right, so we're going to go down and find out. So the trickiest part for these types of questions is figuring out, first of all, what is my stress tensor? Once we have the stress tensor, we can just go into our von Mises formula. So I'm just going to go right here. Sigma is equal to, what is sigma 11? What is sigma 11? Negative 200. It's given right over there. Negative 200. What is sigma 22? Unknown. That's what we're trying to figure out. So sigma 22. What is sigma 33? Negative 200. What are my shear stresses? What are my shear stresses? 0. Am I taking my cylinder and shearing it? No, I'm just compressing it, pulling it. Simple expansion and contraction. So all these are going to be equal to 0. So since I don't have any of those shear components, and I were to look down at my von Mises stress equation, I can almost technically ignore all of that shear stress and kind of that side. So it goes back to the same formula that we had before. So we're going to come down here, and we're just going to plug and chug our way through the question. We know that sigma von Mises is going to be equal to sigma 11 minus sigma 22. Well, sigma 11 was negative 200. Sigma 22, well, we don't know. Sigma 22 squared. Move on to the next one. We have sigma 22 minus sigma 33. So we have sigma 22, it's unknown, minus sigma 33, 200, negative 200. And then finally, we have sigma 11 minus sigma 33. So we have negative 200 minus negative 200. And it's going to be squared. This is divided by 2. And we know that this equation right here is equal to our yield stress. So we know that this is going to be equal to 600. We have one equation, one unknown, which is going to be sigma 22. Question for you guys, is this a linear equation? Is it? Let's put it this way, different way of phrasing. How many values of sigma 22 can result from this equation? Who thinks 1? Who thinks 2? Who thinks 3? Correct answer is 2. If I were to take a cylinder and I'm trying to find how I can yield it, can I yield it in compression? Yes. But could I also yield it in tension? Yes. So when you do these types of equations, you're going to get 2 values for sigma 22. One positive, which means that you're pulling it in tension, and one negative, which means you're yielding it in compression. If we were to scroll up, and I were to give you guys this particular figure, which value would I use, the positive or the negative one? Negative, because as we can see in the picture, I'm compressing my cylinder. So I'm going to come down here and say, okay, once I solve this equation, I get sigma 22 is equal to one of 2 things. The first one is 400 MPa And then the second one is negative 800 MPa. So if I were to take my cylinder, let's pretend the podium is my cylinder, and I were to compress it laterally, if I were to pull it, does it become weaker? Yes. And it makes sense because I'm trying to pull it, and all those forces laterally are also trying to squish it. It's easier to pull. But if I'm trying to compress it, my cylinder naturally wants to expand. But if I'm putting forces to stop it from expanding, it gets a lot stronger. So in this case, it would be 800 MPa to yield it, even though my yield strength is 600 MPa. We do this with concrete all the time. We make sure it can't expand, it becomes a lot stronger. All right, so here's the next one. Based on the Tresca yield criterion, find the yield stress sigma y if the material yields when the 3D stress reaches this. Now, what's the first thing that you guys have to remember when dealing with principal, I just gave it away, when dealing with maximum shear stresses? Principal. Is this already in principal stress format? Yes, because it's diagonal. There's no shear stresses. So my principal stresses are going to be 50, 90, and 0. So all I need to do to find my tau max is just find the maximum of the absolute value between the differences. So we're going to have sigma 1 minus sigma 2 divided by 2. We're going to have sigma 2 minus sigma 3 divided by 2. And then our last one is going to be sigma 2, or sigma 1, sorry, minus sigma 3. Running out of room, divided by 2. So all you guys need to do is plug them in, because we have sigma 1, we have sigma 2, and then we have our sigma 3. So I'm just going to go through here. Absolute value of 50 minus 90 divided by 2. We can have the absolute value of sigma 2 minus sigma 3, so 90 minus 0. All this divided by 2. And then finally, we have 50 minus 0. Option 1, 2, or 3. Which one is going to give me my maximum? 1, 2, or 3? Did I hear 4? 2. What is it going to be? What's my maximum shear stress going to be? 45 MPa. So we know that this right here, this is my maximum. Therefore, tau max is just simply 90 divided by 2, 45 MPa. Now I'm going to scroll up and let's remember what the question says. Based on the Tresca yield criterion, find the yield stress sigma y if the material yields. I want my yield stress. Is 45 my yield stress? No, that's the second trick. When it comes to Tresca, 2 tricks. First one, make sure that you guys are doing principal stresses. The second trick is your tau max is not your yield stress. What is my yield stress? The tau max is 45. 90. My yield stress, sigma y, is 2 multiplied by tau max. So it's equal to 90 MPa. That's the second trick. Remember that your tau max, it's not your yield stress. If I were to give you guys a yield stress and ask you guys, does it fail? Make sure when you take your yield stress, you divide it by 2 to get the maximum shear stress when comparing. That's the trickiest part of these. How are we doing for time? Perfect. We'll go to the last one. Assume that concrete fails when sigma T is 2 MPa and sigma C is 40 MPa. So tension, compression. How many people can a concrete pedestal hold if the people stand on the pedestal or the people hang on the pedestal? So what is A? What's the concrete undergoing if people are standing on the pedestal? Compression. If people are hanging from the pedestal, tension. That's it. So all we have to do in these cases is just compare the stresses we apply to the failure limits. Notice I didn't say von Mises. I didn't say Tresca. This is just a simple, does it fail? Yes or no. So this is when you guys have to kind of remember a little bit back to Civi 270. What is the formula for stress? Force divided by area. No. So sigma is equal to force divided by area. Now, what is my force equal to? I'm given the number of people in kilograms. How do I convert kilograms into a force? Multiply by gravity, and that's for one person. So we know that my total force on something is going to be the number of people multiplied by their weight, or I guess their mass, and then multiplied by gravity to turn it into a weight. So that's going to be my force. The area of the pedestal, it was given. It says that it's 250 by 250. So this is 250 multiplied by 250. Now, just the only thing I can really think that would trick students up is just units. Kilograms multiplied by acceleration, what does that give us? Newtons. Millimeters times millimeters, millimeters squared. This is what I'm getting at. Newtons divided by millimeters squared. What is that for pressure? Who thinks kPa? MPa? It's MPa. So we know that this is already going to give us MPa. And for case A, where it's in compression, we know that the strength is 40 MPa. That's actually pretty typical. So 40 MPa. So all this is equal to 40. Our only unknown is the number of people. And if we solve for it, we get N is equal to 3,641. So that's if it's in compression. If I were to consider the case now where it's in tension, so I can erase the 40 because that's compression, and for tension, it was 2, and I solve this exact same equation, N over here is equal to 182. Big difference. Big difference. This is why you guys don't really see too many concrete cantilevers. Think of all those fun things that you guys see at like the Grand Canyon. You know how they got that big horseshoe thing so you can go and look down? Made of concrete? Concrete's terrible in tension. Terrible in tension. If you guys go look at something that's not pre-stressed and go look underneath, let's say that the roof above us wasn't pre-stressed, probably is, and all these panels were gone. Would I see a bunch of cracks? Yes. Here's another little fun fact. If I have a concrete section, again, we're assuming not pre-stressed, and let's say that our concrete section is 500 millimeters deep. What do you think the cracks go up to? How far up do you think that these cracks go up to on a typical concrete beam? Actually, let me just change the color. Concrete beam, cracked. What do you guys think this distance typically is? Who thinks less than 100? Who thinks, I don't know, around 200? Who thinks greater than 400? Be greater than 400. Isn't that crazy? Most of our concrete beams, if they're not pre-stressed, the majority of the bottom is all in tension. All in tension. That's why we put the steel in. Nice and fun. That's concrete design, as you guys will see. You guys know how to design things yet? It's actually quite simple. If I were to give you guys a simply supported beam with a distributed load, nice and beautiful, could you guys find the maximum moment? Yes. So you guys can find M max. And all you guys have to do when you design a beam is make sure that the moment resistance of the beam is greater than M max. That's it. Now, what happens is there's steel at the bottom of the beam, and then there's compression from the concrete. By compression in the concrete, is that going to create a force? If it's compressing with each other. What happens is this concrete part creates a force this way. My steel creates a force this way. They must be equal because it's in equilibrium, and they're separated by a distance d. If this is a force, which we'll just call F, what happens when I take F times d? That's a moment. This is how you find the moment resistance of a beam. Any beam, concrete, steel, timber, whatever. You just find the forces inside of the beam and take the moment between them. And you just make sure that this right here is greater than this. This is beautiful. Because let's say that I don't want to increase the strength of my concrete. Can I increase my moment resistance without changing F? The distance. If I have a deeper beam and I just separate my steel from my compression concrete, my moment resistance is going up. Isn't that nice? Don't even have to change the strength. So this is where design comes in. Because you're saying, okay, I can save on material costs by not increasing the strength by just making it deep. Well, then the architect gives you garbage. Then they're saying, what are you doing? No, you keep it small. So that's what design is. Finding that nice balance between material costs and keeping the architect nice and happy. It's kind of in between there. So yeah, that's it for today. Thank you guys. I'll see you in the seminar later.